From previous video, we saw we are actually discussing the nonlinear equation in fluid mechanics, and we saw that the continuity equation. Now, in this video, we will discuss the momentum equation. Momentum equation, as you have learned about it in your previous studies, it is about the mass and velocity. How big is the mass? Momentum is high. How fast is the velocity of the object? Momentum is high. So it depends on two variables, m and v. M is the mass and v is the velocity. So the momentum is something, it means that the impact of one object on another object. So this is called the momentum. Now, how the fluid make an impact on some other object. For example, if there is a fluid and it just strikes with the wall, then mostly it actually destroy the wall if the impact is too high. So we need in fluid mechanics we need a momentum equation to discuss the forces and also its impact, inertia, and so on. So let me just go back and write the flux for example, I should first write the equation, general equation, partial Q by partial T plus partial F by partial X is equal to 0, where F is the flux. F is flux. Okay. And we changed this flux, for example, when we changed this flux with U bar density, then we get one equation. When we change this flux with U is variable and density is there, we get continuity equation. Now we want to write momentum equation and we need to change the flux as well. Okay. From here, we see that the momentum is defined like this. It is a vector quantity, in fact, so velocity is a vector, so we write like this. Now we need some quantity. What should we put over here? The first thing which comes into our mind is there should be a mass of the fluid and velocity of the fluid as well. But the problem is, so this momentum, this is the definition of momentum. But the problem is, in fluid mechanics, we talk about the volume. For example, if some of you probably know that in fluid mechanics, we have a volume and we actually we calculate impact of momentum on that volume. From there we actually get the equation. So we need to introduce the volume as well over here. So what we do now, so we do it like this. For example, instead of defining mass, I define over here the density V, and this will be equal to mass velocity divided by volume. So usually we work in volume. So we understood that now that we need a volume rather than the mass. So equation for flux, the first quantity will be the momentum. This is the momentum equation. This is the momentum term. This is the momentum term. But how this momentum will enter into the some volume. For example, if we have some pipe and the quantity that is entering, I describe it rho v, which is the momentum, but it will travel into the this pipe. it requires a velocity. So we multiply this with the velocity v. So it means that we need to introduce the velocity over here. So we add that rho v, and this is equal to rho v square. So the flux will be rho v square. This rho v square is actually coming from the bulk motion of the fluid. But if we have, for example, the water somewhere, we have water, then there are molecules, small molecules, and these molecules collide with each other. When they collide with each other, they generate a pressure. They generate a pressure, right? So it means that there are two terms. One is macroscopic, and another one is microscopic flux. Flux. The momentum is generated when there is molecule imbalance. Then the larger molecule actually make an impact. So there is a momentum due to the pressure as well, and there is a momentum due to the velocity of the fluid as well. Okay, so we need to add the pressure over here. So I add this formally over here, it is pressure. So flux will be due to the momentum which is transported, and then we have the momentum due to the pressure. We put this value over here, and we also replace q is equal to some other value. Okay, so let me just write down the equation for that. Previously we saw that if we have a pipe, for example, we have a pipe like this, x1 and x2, and we measure the quantity by integrating x1 and x2 and the quantity rho u dx. So we have x1, x2, rho u dx. Remember that when we have one dimensional quantity, so we make density which is mass per length. It is mass per length. So we have the this density is mass per length. If I want to change that, how this quantity is changing, we take a derivative with respect to t. That will be equal to the flux that we have introduced, rho u square plus p, and x1 and x2. We take a value over here. After solving this problem, we have rho u, or I should write it like this, partial rho u by partial t plus rho u square plus p x is equal to 0. So that's what we have from the above equation. You just need to find the flux at x1 and x2 like this. For example, we have rho u square plus p at x1, then we have rho u square plus p at x2. So when we solve it, we actually get the answer, right? We already did that. You have to make an integration from that d by dt x1 x2 rho u dx is equal to, then we have, for example, uh, minus rho u square minus p upper value x2, then we have plus rho u square or something like that. We already have it. The video is a bit longer now, so you have to make the you have to introduce here x1 to x2 and this quantity rho u square plus p dx, then these two terms will be added. There is a minus sign. Due to that reason, I want to make it plus on the left hand side, right? So this is the quantity. I should first write it in the consistent manner, partial by partial x rho u square plus p is equal to 0. So that's what we have the momentum equation. Remember that this is not for the for the viscosity. When we have a viscosity, this is a kind of Euler equation. So thank you for watching.